Autoregressive models struggle to scale artist-designed meshes to high triangle counts. We introduce MeshMosaic, a local-to-global framework enabling artist mesh generation with over 100,000 triangles. Most autoregressive methods struggle with long sequences and fine details. They need lots of tokens and don't offer enough quantization granularity. This makes it hard to capture complex geometry and density in meshes, so earlier approaches typically could only handle about 8,000 faces. Here we show the pipeline of MeshMosaic. During inference, our method first applies part field to obtain semantic segmentation of the input shape. The input point cloud is then sampled according to the segmented patches and the original shape. Finally, our approach produces a clean, highly detailed mesh by assembling the generated patches. For single patch level training, shared boundaries are used to ensure that neighboring regions connect smoothly, maintaining coherence and symmetry. Additionally, point clouds are incorporated as conditional inputs at both global and local levels. Specifically, each patch only gets boundary information from the previous patch following BFS order. For example, in this shape, the first patch doesn't have any boundary info since there's nothing before it. The second patch can partially see the boundary of the first, and the third patch is similar. It only gets partial information from its nearest pre-computed patches. Here, we show a gallery results of MeshMosaic that highlight its ability to recover fine details, like bone spurs along the spine and subtle features in the face. Even though the most complex models in our training set have just over 60 patches, MeshMosaic easily handles examples with hundreds of patches. For instance, here's a generation with 223 patches and a total of 127,700 faces. MeshMosaic lets us scale up artist mesh generation by stitching together local patches into detailed high-resolution meshes. It supports flexible mesh density and preserves all those intricate design details. The faces are randomly colored to different blues to highlight the mesh layout. Next, we show visual comparisons with state-of-the-art methods. In the first penguin example, our model captures the shape fully and richly, while other approaches often have issues like face distortion and deformation. The second human example makes the difference even clearer. Only MeshMosaic accurately restores the facial details. Other methods either can't manage such complex shapes or end up smoothing out important features. Now let's look at two geometrically complex examples. For the first one, a brain model, other methods either fail entirely or lose most of the details because they can't handle long sequences or fine quantization. The second example is a sphere with very complex topology, where other methods just can't cope. Only our approach, with its local-to-global framework, is able to accurately recover the original shapes. Finally, we also show how MeshMosaic can turn text or pictures into 3D models. No matter where the shapes come from, whether it's a written description or an image, MeshMosaic is able to convert them into high-quality artist meshes. Thanks for watching. For more details, please refer to our paper.